Welcome to week 5 of inverse methods in heat transfer. In the last few weeks, we saw how to use linear models for forward problems and how to use linear regression in order to solve the inverse problems that occur from linear models. Secondly, we saw that using linear regression, you could write the solution for the unknown parameters using the normal equations. So the normal equations gave us x transpose x times w, which is the unknown parameters, is equal to x transpose y, where x is the design matrix. Now, the same idea was extended to the idea of nonlinear models. And for this, we use nonlinear regression. Nonlinear models means nonlinear in W. Okay. Not nonlinear in X, so nonlinear in W. So with this, we use nonlinear regression. Specifically, we look at the Gauss-Newton algorithm. And it had a form which was very simple, similar to the normal equations, except it was linear in delta W rather than being linear in W. So in this case, we had the equation Z transpose Z delta W equal to Z transpose times effectively delta Y, which we called D. So you can see that essentially, if you take a sort of perturbation of the normal equation in linear, you get the Gauss-Newton algorithm. Now, remember that Z here was del Y hat del W. In fact, you can see that that would be identical to the design matrix in case Y hat is a linear model. Okay, so this is a simple check that you can do. I think I talked about it also in the last week. D, of course, was Y minus Y hat. So these are the two expressions that we have looked so far for inverse methods and also regression. Now, there is a problem which we will see in this. Okay, so these both these models, okay, have problems in what is known as ill-posedness. I'll not get too much into ill-posedness, except for a short example that I'm going to show right now, which will give you this idea a little bit. We are going to show this example in the linear model. Now, this ill-posedness, the actual solution in inverse methods, and this is where inverse methods really take off, is to use something called regularization. This regularization is very important both in inverse methods as well as machine learning, which, as I will argue later when we come to the machine learning type thing, is basically a subset. Okay, so machine learning actually belongs to inverse methods. So we are going to look at a preliminary idea of what this problem is, why this ill-posedness starts, what regularization is in the context of simple linear equations. Okay, so that's what we are going to start. So let's go ahead and do that. So some of the slides that I'm going to show are from the book Pattern Recognition and Machine Learning by Christopher Bishop. It's an excellent book, but it's a very advanced textbook as far as machine learning is concerned. This book is available freely online. This is legally available freely online. So this is kindly been provided by, I think, Christopher Bishop, who heads Microsoft Research, or some portion of Microsoft Research he heads. So he has provided the book entirely freely. And the slides I am showing are actually due to a permission. We have actually taken permission from him in order to provide some of these slides. He's given a blanket permission. I also use this in another course of online course of mine. So this nicely illustrates this problem of both ill-posedness as well as regularization. Before we come there, Let me just briefly talk about the problem and then show the example that I have taken from Bishop's book. So let us say we have a set of data points. Okay, so some points like this. Now, if we don't know physics, if we don't know the physics of the problem and we don't have in mind a specific model that we are going to put, now these points, now you want to find out that function which when added noise to produce this. So for example, y actual is our model plus noise. Okay. Now the hard part and the ill-posedness comes in the fact that what do you ascribe to the function and what do you ascribe to the noise? For example, do we say, as we saw in the linear case also, I showed it to you while showing, let's say, the overfitting, not overfitting, sorry, the normal equations. I showed you that you could fit a line, you could fit a best quadratic, you could fit a best cubic. Now, how do you say which one is y hat? Is it this which is y hat and the rest of it which is noise? Or whether it is the quadratic which is y hat and the rest of it which is noise? Some of it we can guess from physics, but many times it's actually hard to say this. So it is because of this that ill-posedness starts. A similar example would be, I give you an image and it is blurred due to some noise. Now, if you want the original image, you need to know something basic about the image. You need to know maybe it's an image of a cat taken in an open sky or something of that sort. Otherwise, it's hard for you to denoise the image uniquely. So ill-posedness happens because there is no unique solution to this problem of separating out noise from signal. There is a second problem which happens, which I will kind of demonstrate to you during these, which will talk about the stability issue, which I briefly alluded to in the first week. So let's see both these in the example that we are going to take a look at right now. So here it is. Here is a polynomial curve fitting. So these blue dots here that you see here are the original experimental data. So for example, we can assume, so this is t here, let's call this y hat, and this is x. So you measure at x equal to 0, you got some y hat. At x equal to some value, got some y hat. We have given a similar example which could occur within heat transfer or a semi within heat transfer within week 5's assignment. So please take a look at that. So you have this curve. Okay, so you have this curve which is sitting here. I have hidden the original curve and I will show it to you later. I sort of modified the slides which were given by Bishop. So I have hidden the original curve and all you see is the data points. Now remember, all these data points are being generated as your y hat or some model, your y is y hat plus some noise. So let's call this noise. Now what we are going to do in order to find out what the original curve is to fit polynomials of different orders. So for example, m equal to 0 means a straight line polynomial, m equal to 1 means a linear polynomial, m equal to 2 means a quadratic polynomial, etc. We are going to try to fit different polynomials and see which one fits best. Okay, so the hypothesis here with which we are working is the better it fits the original data, the lower the error j, or let's call this e, just to distinguish it from the cost function. It is like the cost function with some mild difference. Okay, so if we take the mean square error of our fit versus the original data, that will tell us how good our fit is. So here is what is expressed here, same thing. Y hat of x comma w is some w naught plus w1 x plus w2 x square. Remember, this is still a linear model. So I'm showing this entire example within the linear model, and we'll see how to modify it for non-linear cases also. Because this is still linear in the w's. Okay. So in short, we can write it as this model. So let's go step by step. We will start with the m equal to 0 case. You can set m equal to 0. You can, how do you find this model? Simple, find out j equal to half y minus y hat square sigma. And let's say y hat is simply w0. Then you minimize j with respect to w naught. In fact, if you do this, if you recall our equations, you will basically get y minus y hot or y w naught sigma. If you actually calculate this, will be 0. This will tell you that w naught will be 1 over m, or sorry, 1 over n in this case, the number of points times sigma of yi. So it will turn out that this line, the constant line which you are saying is the model. This is our new model. Our model now is, this is y hat. That is, we are saying regardless of what x is, my prediction is going to be this, and everything else is noise. Okay, so the original signal was a straight line, but noise, random noise added to it. Now, this doesn't look like a great model. We can look at it intuitively and say, maybe I can do slightly better. So we go to the next case and we fit a first order polynomial. Okay, so now remember, our first order polynomial is simply a linear fit, y hat equal to w naught plus w1x, and then optimize this. And in fact, you can use this normal equations approach. In fact, I would encourage you try this during the exercise for this week. We have given some data set just for you to replicate this kind of effect. So you can try this and you get some W0 and W1. This looks better. Okay, it looks like if you look at, for example, R square, etc., it looks better. Lower error, okay, than it was before. In the previous slide, you can see errors are much higher. You can see errors are much lower. And this fits better. Okay, overall, you can look at it and say, okay, this fits better. So we can keep going. You say, why stop at 1? I'm not shown 2, but let's say we go to 3. Okay, so the green stuff that you see here is the hidden model or the hidden original data, which I have kind of removed. You can see that some of it still kind of appears here. So ignore that for now. Okay, so ignore that for now. I'll reveal this towards the end of this video. So this is m equal to 3. This looks like it's even better. It kind of captures the trend even better, but you might be slightly suspicious, but definitely lower error. Okay, so again, you can see 3 points are almost exactly fit compared to the linear case, which had more noise. This has less noise. So now you go really, really greedy and say, I add a really, really high order polynomial. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can always add a 9th degree polynomial here. And here I put a 9th degree polynomial. Now let's see what happens. If you look at it, it has actually fit every point exactly. But the question is this good? Should you really fit every point exactly? If I give you a slab temperature data which looks like this, you know the function is linear. If I start predicting temperature like this and I find heat transfer using the gradient, won't it be really bad? Okay, so in this case, you might actually get a very high gradient when you actually want a slightly lower gradient. So see this. Look at how the function varies. This is part of the stability problem. That is, if I change the data a little bit, so if I put slight noise to this data, you can imagine that the function will change drastically. Okay. So small changes in X or data lead to large changes in Y hat. Okay, so if I go from this position to a slightly different position, see the change in Y hat. It's just huge. This is typically a stability issue, and especially when our thermocouples and our measurement instruments are noisy, this is completely undesirable. So now let me show you what the original function looks like. Okay. Okay, so the original function looks like this. This is what was added noise to. You can see that, let's say there was a sinusoidal temperature distribution, and due to thermocouples or due to inherent noise in the system, there is some variation. Okay, so there is some variation in the data. But when you do this, you can see that even though error for the 9th degree polynomial is 0, it is not a good fit. So just driving the error to 0 or driving the cost function to 0 is not really as important as putting the model which is of the right order. Now let's compare this with the 3rd degree polynomial. As I promised, I will now show what this looks like. Now, if you compare what the 3rd degree polynomial looks like versus what the 9th degree polynomial looks like, the 3rd degree polynomial is not a perfect fit, but is stable. It's more robust. What do you mean by stable? Suppose I find dt dx here. This is still going to be approximately the same as what my model predicts. So this is reality. Let me write that down. So this is reality, ground truth, experiment. Whereas this is the model. So you can see that model slopes are much closer to the original slope here compared to here. Look at this. Okay, so if you see the slope here is much lower compared to this. So it will seriously over predict heat transfer. When you see a model which E is 0, but the other quantities, it actually predicts poorly. So this is not a robust model. Not robust. This is unstable. Now, why does this happen? This happens due to the inherent ill-posedness of the problem. Ill-posedness in that we don't know what the function varies like in the middle. Okay, for the same data set, I can give many different function fits. So that is the reason why ill-posedness starts. Okay. Now, within this machine learning literature, this problem has a particular name. This is that error is 0 or error is low, but the fit is bad, means it's called overfitting. Okay. So overfitting will behave in the following way. Overfitting will behave like this. So this is called training. Training means original data set. So remember the original 9 points that I had. I will train, I'll find the error. You can see that when the model is of a low order, so on the x-axis is the order of the model, on the y-axis is the error that we found. So when 0th degree model has a high error, 3rd degree model has a very low error, and that keeps on going, and 9th degree model actually has completely 0 error. But even though the error is 0, there is something else which is high, which is test. So I'll explain that. Test means this. You, instead of having only 9 points, let's say you had 12, and 3 of them you held back. Okay, you held back in the sense, just like a teacher. A teacher will show you some examples during class, that is the training set. And when I hold a final exam, I would have held out some few questions behind. So if somebody mugged up, just memorized the training, they would do very well on the example problems, but they will do very poorly in the test. So how do we see the same example here? Maybe my original data set is at these points, the original 9 points that I showed you, here. But my test point could be here. Okay, so I could have a test point here, and I know that the original data is here, but prediction is very far off. So this will give you a high error. Okay, so you can see this. It was doing well in training and testing in 3rd. For example, if I held back this data point, okay, you'll see actually the way the prediction I made and the original is actually fairly close, as against, once again, something like this. This point here is the actual data and prediction is way down. Okay, so that's why typically this is the graph that you will see in overfitting within machine learning. If time permits, I'll show this later, but this is true even for the linear regression example that we did. So the normal equation solution will give us these bad results for problems in case you put too high. Okay, so order of model, or this is called complexity of model in case of nonlinear models. Too many parameters, too many knobs to turn was too high. So this leads to overfitting. This, on the other hand, is underfitting. Okay, I could have gone a little bit better. So that is underfitting. So this is known as the classical bias variance problem, and we will come to that again later on when we come to the machine learning portions of this course. So how do we cure this problem? So for this, we start looking at the coefficients of what the various degree polynomials are, and this gives us a clue. And we will use this idea to improve our nonlinear Gauss-Newton also. So let's look at what the values of the coefficient are for the case of linear regression with various polynomial degrees. So what you see here are the various coefficients. So for example, W0 optimum, W1 optimum, etc. Of course, this is the 0th order model. This is the first degree linear model. This is the cubic model. And this is our so-called best fit. Notice a certain phenomenon. Look at the size of the coefficients or of the parameters. Wi. So these two are well balanced. These slightly start varying. This travels a huge order of magnitude. So this was small, this is really large. So this has both large and small coefficients. So this is just true observational. Okay, this always happens when there is overfitting. When there is overfitting, your W will travel through a large range of values. Okay. Now, let us see if we can cure this. So, can we cure overfitting? So, I'll show you two different cures. The first cure is kind of a semi-practical. The last cure is the one that we are coming to, which is called regularization. So, the first cure is this. Increase data size. Another way of saying this is, suppose you do a few problems, example problems, and you do very poorly in exam. Obviously, you are never going to know what the exam questions are. But one thing you can do is solve more example problems. So we are still going to stick with the same order polynomial, same complexity as before, but we are going to increase the number of data points. Training data points increased. So we fit a 9th order polynomial for 15 data points. This is still easy because our original equation still works. Okay, our normal equation approach still works. This will be 10 cross 1. This will be 10 cross 10. And this will also be 10 cross 1. I request you to do this exercise by yourself. For example, what will be the size of Y? Y itself will be 15 cross 1 because there are 15 data points. But X transpose will actually give you 10 cross 15. So please check this out and do this problem. Okay, take some fake examples and do this problem. It's an interesting exercise problem for you, just to understand what the matrix sizes are like. Okay, so we come here, we see that the fit is slightly better. Okay, it is still overfitting. It is still not as good as the original line, but you can see that this is less noisy. So the student who has done more example problems, these are all example problems. If I test somewhere at a new problem, it doesn't do so poorly as before. So again, I introduce a new data point which was not there and check the gap between what is true and what is predicted is still not as high. Okay, so less noisy, lower test error. Okay. All right. Now, suppose I increase it further and put a lot of, so this person has done lots and lots of exercise problems. Now you can see this is a robust fit. It's still the 9th order polynomial, but you are fitting it through 100 points. So that's like lots of data points. Obviously, you can't fit it perfectly. No ninth order polynomial will go through all these data points. So this is just going to go through, and this best fit is actually much better than the original ninth order polynomial. So what we infer from this is number of data points should be large in comparison to the complexity of the model. So we can't just say ninth order polynomial is high. Ninth order polynomial is high in case you have only 10 points. Okay, but it is not high in case you have 100 points. In that case, it actually fits really well. So this is one way of solving overfitting, that is increase training data points. But as you know, we have only a few sensors in heat transfer or any such problem. How are you going to increase data points? I mean, that is the number of data points you have and you want a model. So most of the times, this is usually not possible. Usually it is not possible to do this. So then you have the second solution called regularization. Okay. So this is the standard solution to overfitting. And the idea is very simple. You penalize large coefficient values. What does that mean? There are different ways of looking at regularization. I am showing you one way, which is standard and linear. I'll show you a couple of more ways in the next video when we come to nonlinear regression and how we actually do regularization there. So penalize large coefficient values means, remember in our slide here, we saw these W values, some of these were very, very large. Whereas in the perfect model, most of the W values are roughly small. So you say, okay, I am going to make a new loss function. This is called E here. I am going to call it J. So J is the J due to fitting data. So let's call this Y hat here, plus some cost or penalty for large W values. So J for fitting data looks like half yi minus y hat I square. So this only tells us how well data fits model. So that we saw anyway. But this tells if coefficients are large, you have to pay a price. That's basically what the second part says. So if coefficients are large, you pay a price. And that price is given by a very simple term. This I have told you earlier too. This simply means sigma of Wi square. For example, you can have W0 square plus W1 square up till Wn square. Okay, so as many coefficients there are, you just add these costs and you multiply by a factor up front. This is called the regularization parameter. So the regularization parameter, lambda, you can vary this. And this is what is known as a hyperparameter, much like our learning rate alpha. All you do is you keep on changing lambda and see what happens to your prediction as you vary lambda. Okay. Now, there are specific tricks to do this, and that's slightly beyond the limit of this course, but I might touch upon this once again if I come to the machine learning portions. But the idea here is clear, and it should become clearer as I show later on. Suppose you have a fit. Okay, so you have these data points that you want to fit, and you are choosing between multiple models. Now, as the model tries to fit these data points more and more perfectly, what will happen is this portion will go down. Okay, so J fit will go down. But what will happen invariably is if the number of data points is too few, then J coefficient will go up. Why? Because you will require larger and larger W. So the idea is somewhere in the middle, you will automatically hit an optimum. And this is kind of sort of like a damping term. It damps out large oscillations. Okay, so we will see this effect, well, not quite explicitly, but we'll see this effect also later on this week when I come to the nonlinear equivalents of this. This kind of damping is called, has several names. It's called Tikhonov, after the name of a scientist, Tikhonov regularization. It's also called ridge regression. It has other names also. It's also called L2 regularization. So I'll come to L1 regularization when we come to machine learning. So all these three names are equivalent names as far as we are concerned. All it boils down to is to changing our loss function to the usual loss function plus lambda times sigma of the weights of the coefficients divided by 2, and this you will have to play with. Now, there is a significant advantage of playing with lambda rather than playing with the order. In this case, as you will see also coming to neural networks, you can simply fix the nonlinear model and you are just changing a small penalty term. As it turns out, this has a huge number of different interpretations. We will see 2 to 3 different interpretations, a couple in the next video and one later on when we come to probabilistic method. So this one simple term, addition of one simple penalty term, has several meanings within both inverse methods as well as machine learning. But let me show you the effect of doing so. So let us say we set lambda equal to 0. Okay, so if we set lambda equal to 0, this means no damping, okay, so, or no regularization. So you will get the same coefficients as before. These are the original coefficients. You saw there is a huge range of these values here. So this is, of course, a bad fit. It gives you low J of the fit, and it gives you high coefficient fit. Okay. Now you come here. Log lambda is minus 18 means lambda is e to the power minus 18. When I do my experiments a couple of videos from now, I will go in powers of 10. But since you are giving ln lambda here, it makes sense to go in powers of e being our 2.7 e power 1. Okay. So now you see when you set log lambda equal to minus 18, the coefficients are uniform, don't vary much. So it will be useful to see what it looks like. But currently all we are looking at is the intuition that we don't want coefficients to vary very much. Generally, observationally, there's no direct logic that I can give you here. But observationally, when the coefficients are all equally scaled, it turns out that your function is not very noisy. Now, here is log lambda equal to 0. This, of course, means lambda equal to 1. This is a high value, high regularization. Notice higher coefs go to 0. So which means we expect it to perform about as well as a lower order model. This would be a higher degree model. This is a lower order model, and this is somewhere intermediate. So let's see what it looks like physically. Here is the high regularization. And look at what it looks like. It almost looks like the m equal to 0 model, but we still used an m equal to 9 model. Please notice we have always we are not putting lower order models here. We are always using 9th order polynomial, but the optimum W is found out by adding this extra cost. So if you use the original full 9th order, it will say, no, that will not work because you will have to pay too much penalty for these coefficients. Okay. So if the penalty is, it's highly penalized, then it just becomes like this function. You can compare this with the m equal to 0 model. It will look somewhat similar. Okay, so you can see the m equal to 0 model, and you can compare it with the original also. Okay, so you will see this is approximately similar to the m equal to 0 model. Now, if I take that intermediate case, I already know what it looks like when I look at the lambda equal to 0 case, because that's just the bad fit. But if I look at the intermediate case, that will look slightly better, as you can see shortly. As you can see here, when you use the intermediate model, you see a very, very nice fit. Okay. So this almost looks like the m equal to 3 fit that we had earlier. Okay. So if you go back, you see the third order polynomial and the intermediate fit. Even though here we had stopped our polynomial at third, here on the other hand, we let it be a ninth order polynomial, but we just changed the regularization parameter. So the moment you change the regularization parameter, you are able to travel the entire thing from a very bad model to a decent model to a very high model. And all of it depends only on the one single parameter, which is lambda. So if you vary lambda, you can actually keep the model fixed and just vary the regularization. That's the basic idea. Okay, so this gives you intuition for why we will use this kind of damping within nonlinear. So what we looked at in this video was just this for linear models, specifically polynomial models. The same trick tends to work very, very well in nonlinear models also when there are a large number of parameters. So I'm going to do the theory in the next video, and I'll finally, in the last video, I'll show you a code. As I said at the beginning of this video, we are actually not going to show you a practical case where we apply it, because you still have to do the calculations by hand. So I'm stopping with a small number of parameters like A and B, or just 2 parameters. But as you go to a large number of parameters, this kind of damping, this kind of regularization becomes inevitable and very, very useful, as we will see when we come to the neural networks case. So thank you. I'll see you in the next video for nonlinear regression, how we modify it using similar regularization.